So we're going to start with trying to graph the function f of x equals x cubed minus 1 divided by x minus 1. And to do that, we're going to use all of the standard graphing techniques that we've learned so far. However, there's going to be a problem when we get to x equals 1. To see what's going on as x approaches 1, we make a table. We want to approach 1 from the left, and we want to approach 1 from the right. So we want to pick values that get closer and closer to the number 1. And then we evaluate each x value. So 0.75, we plug that in, and we're going to get 2.313. We do that for all the values that we picked, and notice that as we get closer and closer to 1 from either direction, f of x is going to get closer and closer to 3. Here we have a graph of f of x, and notice that it's a parabola, but it's going to have a hole at the point 1, 3. So we can informally say that the limit as x approaches 1 of the function f of x is equal to, well, what value are we approaching as we get closer and closer to 1? As we get closer and closer to 1 from both directions, f of x is getting closer and closer to the number 3. So it equals 3. In this example, we're going to try to evaluate the function f of x equals x divided by square root x plus 1 minus 1 at several x values near 0, and we're going to use that result to estimate what the limit is. So I have already made a table right here, and right in the middle I'm going to write the number 0. And I'm going to approach the number 0 from the right and from the left. So the x values that I'm going to use on the left are going to be negative 0.003, and then negative 0.002, and then negative 0.001. So I'm getting closer and closer to 0 from the left-hand side. And then on the right-hand side, I'm going to use 0.001, 0.002, and 0.003. Once I have decided my x values, I'm going to evaluate the function at each value. So when I plug in negative 0.003 into this function, I get the value 1.9985, 1.9985. If I plug in negative 0.002 into the function, I get 1.999. Do the same thing for the other value, I get 1.9995. And now if I try putting 0, I'm going to get an undefined answer, so I'm going to put a question mark there. And then I'm going to do the same thing for the positive value. So if I plug in 0.001, I get the value 2.005. Actually, it's 2.005. Plug in 0.002, I get 2.001. And then the last value, I'm going to get 2.0015. Now, from this table, we can estimate what the limit is. So we write the limit as x approaches 0. And then after the limit statement, there has to be a function. So the limit of this function, x over square root x plus 1 minus 1. So the limit as x approaches 0 of f of x is approximately, what values are we approaching? Well, from the left-hand side, it looks like we're approaching the number 2. From the right-hand side, it looks like we're also approaching the number 2. So we can estimate that the limit as x goes to 0 of f of x is 2. Here is a graph of f of x. Notice that the value is going to be 1 unless x is equal to 2. In that case, the value is going to be 0. But we can ask ourselves, what is the limit as x approaches 2 of the function f of x? What is that going to equal to? Now, as we get closer and closer to the value 2, as we get closer to 2 from the left, and as we get closer to 2 from the right, we're going to be approaching the number 1. So the limit as x approaches 2 of the function is equal to 1. Now, notice that the function at 2 is not 1. F of 2 is equal to 0. But the limit and what the function actually is at that particular value don't always have to be the same thing. We're approaching 1 as we get closer and closer and closer to 2, even though the function at 2 is 0. So, when will a limit fail to exist? When are we never going to have a limit? There's going to be 3 cases. The first case is if you have different left and right behavior. This is what the graph of the absolute value of x divided by x looks like. So, let's ask ourselves, what is happening to our y values as x gets closer and closer to 0? So as we're getting closer and closer to 0 from the left-hand side, we're always going to be at -1. As we get closer and closer to 0 from the right-hand side, we're going to get closer and closer to +1. So this is a case where the left and right behavior are not equal to each other. So this is a case where the limit as x goes to 0 of this function, we say, does not exist. And the reason why it doesn't exist is because the left and right behavior are giving me 2 different numbers. This is the graph of 1 over x squared. What's happening as we approach 0? Well, as we're approaching 0 from the left-hand side, our y values are getting bigger and bigger and bigger. In fact, our y values are going towards infinity. As I approach my 0 value from the right-hand side, my y values are also going towards infinity. So you might be tempted to conclude that the limit as x goes to 0 of 1 over x squared is equal to infinity. After all, I just finished telling you that if the right and left behavior are not the same thing, then that's a case where you don't have a limit. But this is actually wrong. You can't set a limit equal to infinity. Infinity is not a number. So what you say is, if you get something like this, instead of saying the limit as x goes to 0 of 1 over x squared is equal to infinity, you say that it tends towards infinity, or a preferred answer is to say that this limit does not exist. And it does not exist because it's showing an unbounded behavior. In other words, you're going to get infinity as your limit. And you can't set it equal to infinity. It's not a number. The last example of where a limit fails to exist is called this oscillating behavior case. So I want to show that the limit as x approaches 0 of the function sine of 1 over x does not exist. I have a table right here, and I'm going to pick values that get closer and closer to 0. So I'm going to start with 2 over pi, and then 2 over 3 pi, 2 over 5 pi, 2 over 7 pi, 2 over 9 pi, and then 2 over 11 pi. When I plug in 2 over pi into sine of 1 over x, I'm going to get the value 1. If I plug in 2 over 3 pi into the function, I'm going to get the value -1. If I plug in 2 over 5 pi into sine of 1 over x, I'm going to get the value 1. Plug in the next value, I'm going to get -1. Plug in the next value, I'm going to get +1. Plug in the last value, I'm going to get -1. So notice that for every single x value that gets closer and closer to 0, my f of x is not getting closer to any number. It's oscillating, or it's going back and forth between the values 1 and -1. 1 and -1. So there is never a value there's never a y value that we are approaching as we get closer and closer to 0 from either direction. I could have shown you as we approach from negative values, and it would have been the same thing. It would have been 1, -1, 1, -1, 1, -1. In conclusion, we learned two things today. How to find limits using tables and graphs, and when will a limit fail to exist. It will fail to exist if there's a different left and right behavior. In other words, if you approach C, but as you approach C from the right and from the left, you're getting two different values. That's a case where the limit fails to exist. The limit can also fail to exist if you get a limit that equals infinity. Remember, we cannot set anything equal to infinity. So that's an unbounded behavior. The limit does not exist. Or if the value, as we get closer and closer to C, if the value goes back and forth between two numbers. That's another case where the limit fails to exist.